If you start an AHU retrofit by asking, which EC fan has the same diameter, you may buy a fan that fits the opening but misses the duty. A retrofit is not a motor swap. It is a controlled rebuild of the fan section, with 6 constraints that must agree. First, measure what the existing unit is actually doing. Record airflow, fan static or total pressure, electrical input, speed command, and the pressure boundary. Add the operating schedule, filter condition, and any recurring noise or maintenance problem. A nameplate is useful, but measured duty is the starting evidence. Next, draw the boundary. Are you replacing only the fan plus discharge plenum, or the complete fan section? Do not compare a catalog free air maximum with installed static pressure. Keep airflow, pressure type, air density, and test arrangement on the same basis. One design point is not enough. Create at least 3, normal load, low load, and the worst resistance condition, often a loaded filter. For a variable air volume unit, add the hours spent in each range. That profile is what determines control range and annual input energy. The maximum point only checks capacity. Now open the cabinet. Measure depth, inlet clearance, discharge to coil spacing, mounting points, cable exits, and the removal path. A plug fan needs a clean, uniform inlet and room for discharge flow to develop. A mechanical fit can still create an aerodynamic system effect. Decide whether the job needs one larger EC plug fan or a modular array. An array can help when the cabinet is shallow, airflow distribution across the coil matters, or service continuity is required. But it also adds wiring, protection, controls, and interaction between fans. Choose the architecture from the AHU constraints, not from a fashionable layout. Then place every duty point on the manufacturer's curve. Confirm that each point is inside the permitted operating region and check speed, input power, current, temperature and sound at that point. For example, the current Longwell LWBE3G450-102NT-20-00 sheet identifies a 380-volt, 3-phase EC backward curved fan. Its maxima are boundaries, not a retrofit selection. The project duty must be reviewed on the curve. Check supply voltage and frequency, protective earth, branch protection, maximum current, cable routing and the finished AHU's electrical requirements. Do not assume EC means the old starter can stay. Document what is removed, what is retained, and which protective functions live inside the fan versus the panel. Make a point-to-point control map, run command, speed feedback, fault relay, network address, and loss of signal behavior. The example LWBE3G450 sheet lists 0 to 10 volt, PWM, and RS485 options, but the exact ordered variant and project sequence still have to be confirmed. Test minimum speed, stop, restart and fail-safe behavior before handover. Installation geometry can shift the operating point. A blocked inlet, abrupt transition, or poor discharge spacing produces system effect. The installed system may deliver less air than the laboratory curve suggests. Preserve inlet uniformity, check the inlet ring relationship, and evaluate airflow distribution across the downstream coil. Finally, compare before and after on the same measurement boundary. Verify airflow, pressure, electrical input, sound and vibration at normal, low load and worst resistance conditions. Prove the control and failure sequence. Only then calculate project savings from measured power and real operating hours. So the right EC fan is the one whose curve, envelope, power, controls, air path and service plan all pass together, not the one with the closest diameter or the biggest maximum airflow. For an engineering review, send the existing model, 3 duty points, cabinet dimensions, voltage, control sequence and installation photos.